right, class, welcome to Calculus 1. We're going to start right off at the beginning in Chapter 1. And the first thing you might be asking yourself is, what is calculus? So calculus is the math that describes the changes in a function. So we're going to need to start by making sure we have a solid understanding of what a function is and all the different properties that these functions have. And you've probably seen functions before in previous math classes. Actually, I know you have, but you haven't maybe called them functions. So let's take a look at those. So a relation is any set of ordered pairs. So any set of ordered pairs on the coordinate plane, where we've got our x, y coordinate plane. Here's our x-axis, here's our y-axis. And a function is any relation where each distinct x value has exactly one y value. Now, what does that mean? Well, the easiest way I've found to discuss this subject is by talking about a vending machine. Okay, how do vending machines work? You push a button, you get out Doritos. You push another button, you get out, I think that's an apple. Who puts an apple in a vending machine? So how is this a good way to describe relations? So think about what something needs in order to function. Okay, let's go back to our vending machine. I've got a couple buttons on my vending machine, and I call those my inputs or my independent variable, my x values. And I've got some outputs, and those are going to be what's in the vending machine, our dependent variable. Let's say I have chips, let's say I have a cookie, and let's say I have an apple, because our vending machine is very healthy. So if I push C, let's say I get chips. If I push D, let's say I get an apple. And let's say if I push E, I get a cookie. Let's think about what it means for something to function. Does this vending machine function? Yeah, it does. What if I change my vending machine up a little bit? And that's going to require me to release a little bit. There we go. Okay, so now what if I have both D and E going to cookie? So I push C, I get chips. I push D, I get a cookie. I push E, I get a cookie. Does this vending machine still function? Yes, right? Each X value has exactly one Y value. Let's take a look at something that wouldn't function. So this functions. Let's make an example that doesn't function. So I've got my same vending machine. Oops. We've got chips, cookie, and an apple. What if I have C go to chips, C go to cookie, and E go to apple? If I push this C button right here, what am I going to get out? I don't know. That's because this X value doesn't have exactly one Y value. It has two different Y values. So this is an example of something that's not a function. So let's go ahead and look at a few examples and state whether these relations are functions. Okay, so let's take a look at relation A. So in relation A is going to be in blue. I have 1, 2, and 3 as my X values, and I have 4, 5, 6 as my Y values. I have 1 go to 4, 2 go to 5, and 3 go to 6. Is this a function? Yes, this is a function because each X has exactly one Y value. All right, let's take a look at B. I have my X values of 1, 2, 3, and my Y values of 4, 4, and 6. Now, I do not need to write 4 twice, even though it shows up twice, right? Because it only appears on the number line, right? Because this coordinates to our XY plane. 4 as a Y value only appears on the number line once. So I have 1 going to 4, 2 going to 4, and 3 going to 6. Now my question is, does this vending machine work? If I push 1, I get out of 4. If I push 2, I get out of 4. If I push 3, I get out of 6. So this vending machine would function. So this is a function. All right, let's take a look at one last example. I have here relation C. I have x values of 1 and 3 and y values of 4, 5, 6. I have 1 going to 4, 1 going to 5, and 3 going to 6. Does this relation define a function? No. What happens if I push 1? Do I get out of 4 or do I get out of 5? No, that's going to cause our vending machine to break. So this is not a function. So a function consists of a set of inputs and a set of outputs and a rule for assigning each input x value to an output y value. The rule of all functions is going to be an equation. Okay? Our input's all possible x values, and we call this the domain. And our output is all possible y values, and we call this the range. So, like I mentioned earlier when discussing whether or not relations were functions, x is our independent variable because it's the input. That's kind of how I remember it. Independent variable because it's input. And y is the dependent variable because it depends on what x is. If we don't know what x is, we can't solve for y. And we say y is a function of x, so symbolically we write that f of x. That just kind of denotes that, okay, this is a function in the variable x. So there's some quick terminology. Again, if you need to go back and review, these PowerPoints are posted on our Canvas site. Now we can determine whether or not a graph of a function is a graph is a function. A graph is a function using the vertical line test. So given our graph, if every vertical line that may be drawn intersects the graph no more than once, then f is a function. And if any vertical line represents the graph more than once, then f does not represent a function. So let's take a look at some examples. So here we have some functions. If I was to draw vertical lines, each x has exactly one y value in all of these cases. So these are functions. They pass the vertical line test. These are not functions. If we take a look right here, I have 2 y values for my 1 x value. Same thing with the graph of a circle. I have 2 y values for 1 x value. Here I've got 3, definitely not a function. And here I've got 2 as well. So these are something that's not functions. So you can test whether or not a graph is of a function with the vertical line test. Given a function, we can also find the zeros of our functions, and these are going to be our x-intercepts. So if I have my coordinate plane, my zeros are every spot where my graph, let's draw a graph. Woo. My zeros are every part where my graph covers the x-axis. So where I've circled right here, these would be our zeros. And we can calculate zeros by setting f of x equal to 0. Now it's important to note that functions can have 0, 1, or multiple x-intercepts. In the example I drew, we have 3. So let's take a look at these, and while we're thinking about how many zeros they have and finding their zeros, I want us to imagine what the graph looks like in order for us to help determine how many zeros they'd have. So if I have f of x equals 3, right? Remember f of x equals y, so this is y equals 3. What does that graph look like? Well, y equals 3 is the graph of a horizontal line. Do horizontal lines have any zeros? No, because they're parallel to the x-axis, they never intercept. So this has 0 x-intercepts. How about if I have 2x minus 1? What's this graph going to look like? Well, this graph is going to look like a line with positive slope that intersects the y-axis at -1. So this is going to be a graph that looks like a line. I'm just going to roughly sketch it here. Here's number 2. Here's our line. So this is going to have one x-intercept. Next, f of x equals x squared minus 3. What is that graph going to look like? What type of function is that? So x squared minus 3, that's an example of a quadratic function. Its graph is going to look like a parabola. That's these big U-shaped guys. And it's been shifted down 3, and we'll talk more about that later. But this is going to have 2 x-intercepts. I'm sure you've noticed a trend. So the degree on this x is a 1, and it has 1 x-intercept. The degree of x here is a 2, and it's going to have 2 x-intercepts. So the number of zeros is at most the degree of your polynomial. Note, even if I have, let's say I have x squared plus 4, this would start above the y-axis, so this has 0 x-intercepts, okay? It can have at most 2. All right, next let's look at the graph x squared minus 9, okay? Why don't we go ahead and sketch that out? If I wasn't trying to graph this, I could just make a table of some x values, right? X, y. When x is 0, y is 9. Sorry, negative 9. When x is 1, y is negative 8. And when x is negative 1, y is negative 8. So I'm going to have a graph that starts down here at negative 9 and looks like this. Okay? I want to talk about when this function is increasing and decreasing. In this case, the graph of this function is decreasing from negative infinity all the way to 0, right? This is where my slope looks like it's going downhill. And we say the function is increasing from 0 to infinity because this is where it's rising. This is where it's going uphill, okay? And we can call this section on the number line where it's increasing or decreasing, we're going to call that an interval. Now, what's really nice about functions and is just like real numbers is that they can be added, subtracted, multiplied, and divided. So if I have two functions, then for every x in the domain of both f and g, we define the new domain as where they intersect. Okay, so let's take a look at a few examples. So keeping in mind that the domain of these functions is going to be the intersection, why don't we go ahead and practice by adding two functions. So I have f of x equals x squared plus 3x plus 4, and g of x equals negative 2x minus 1. Now, what's the domain of each of these functions? Well, the domain of x squared plus 3x plus 4, if we think about what this looks like, this is a graph of a parabola, right? And parabolas are kind of shaped like this. So its domain goes from negative infinity to positive infinity. Next, I have g of x, which is negative 2x minus 1. That graph is a line with negative slope, right? And its domain is also from negative infinity to positive infinity. So I find when looking at domains of functions, we need to be really careful in how we approach these, and the best thing to always do is visualize what this graph of a function looks like. So now we can go ahead and add these. If I have f plus g of x, that's going to equal x squared plus 3x plus 4 minus 2x minus 1. And now we need to combine like terms. So I take x squared, 3x minus 2x is x, 4 minus 1 is 3, and here I have my new function. Now the domain of this function is going to be where our two domains intersect, our domain of f and our domain of g. Well, because they are the exact same set, they're all real numbers, they are going to intersect over all real numbers. So our domain is still from negative infinity to positive infinity. And you could kind of see that by taking a look at the fact that when we added these two functions, we got out a quadratic function that looks like a parabola. So let's take a look at subtracting functions. Now, it's going to have the same domain as our previous function because, again, we're looking for the intersection of these two domains. So I know our domain of our function is going to be from negative infinity to positive infinity. Okay? Now we can go ahead and subtract. So if I take f minus g of x, I'm going to take f of x, which is x squared plus 3x plus 4 minus g of x. Now I'm going to have to go ahead and distribute that negative. So I have x squared plus 3x plus 4 plus 2x plus 1. And now I can combine like terms, x squared plus 5x plus 5. So here we have f minus g of x. This is still a function. Its graph looks like a quadratic parabola. Things can get a little more complicated when we're multiplying functions. Still, our domain is going to be the intersection of these two. So our domain is still from negative infinity to positive infinity. But I'm going to have to do an extended version of FOIL in order to multiply these together. So if I have fg of x, that's the same as x squared plus 3x plus 4 times negative 2x minus 1. So I'm going to have to go ahead and make sure that every term of my first polynomial gets multiplied by every term of my second polynomial. So I'm going to take x squared times negative 2x, that gives me negative 2x cubed, and then x squared times negative 1, that gives me a negative x squared. So I multiplied x squared by each term in that binomial. Now I take 3x, so I have 3x times negative 2x gives me a negative 6x, 3x times squared. 3x times negative 1 gives me a negative 3x. 4 times negative 2x gives me negative 8x, and 4 times negative 1 gives me a negative 4. Now I can combine like terms. So I have negative 2x cubed minus 7x squared minus 11x minus 4. So my resulting is a cubic. Remember the graphs, Something to keep in mind is that the graphs of cubic equations always this one's negative, so it's going to go the other way. Look like this, and their domain is negative infinity to positive infinity. So the domain of these two functions multiplied together being the intersection makes sense. Things get a little more complicated when we're dividing functions because remember, in math, we can never divide by 0. So why don't we go ahead and divide these functions, and then we'll see what we can do. So I have f of g is going to be x squared plus 3x plus 4 over negative 2x minus 1. And what I need to do is I need to go ahead and factor these, right? Let's go ahead and factor, get some good practice. I have negative 1, or just a negative 2x plus 1. And then for my numerator, I need the factors of 4 that add up to 3. There actually aren't any, so that's going to be pretty complicated. So we're just going to leave this as is. We need the quadratic formula to pull that apart, which we're going to discuss in section 1.4. So how to factor these is coming. One thing I need to do, though, is I know I can never divide by 0. So that means my denominator can never equal 0. So in order to determine what values are going to be left out of my domain, I need to set my denominator equal to 0. So we set our denominator equal to 0 and solve for x. So I have negative 2x equals 0, typo. Negative 2x equals 1. I go ahead and divide both sides by negative 2. I get x equals negative 1/2. Right? So this value cannot occur. This cannot be part of our domain. So our domain is going to be, if we wanted to write it in set notation, all values of x such that x doesn't equal negative 1/2. Or you can write it in interval notation. So my domain goes from negative infinity to negative 1/2. It skips over 1/2, and then it goes from negative 1/2 to positive infinity.